So let's go ahead and get started. Today what I wanted to do is talk to you about how we determine the distance to the nearest stars, because it's not like we can just go out and measure them with a ruler or bounce light off them or something like that. So we need to talk about something called the distance ladder, which is how we get from knowing the size of our planet to the size of the solar system to the size of the distant stars. And it's a pretty interesting story because we've managed to figure this out through about 5,000 years of experimentation to figure out how big the universe is. And we've gone from the Greeks to modern telescopes. I guess, but that's probably over 2,000 years it's taken us to figure out everything from the size of our planet to the size of the universe itself. So let's go ahead and talk about just the part where we go from our planet to the nearest stars, and then the activity you all are going to do for next week is determining the distance to the nearest stars using something called parallax. And we'll talk a little bit about parallax at the end of this discussion here. All right, so first of all, let me fire up this presentation. Okay, so if you take a look at the stars, we've already talked about how we can determine things like their color and their temperature just by looking at them, and we can determine how bright they appear to be, and we can determine their composition by looking at their spectrum. But if you look at this star field right in front of us here, you can't really tell just by looking at a star how far away it is. If you look at this star, this is a big blue star, big bright blue star. Is it bright or is it close? We don't know. If this red star is bright or close, you can't tell just by looking at it. So we have to figure out a way to get a measurement to the distance. Once we know the distance to the stars, we can figure out, is it intrinsically bright, is it close by, or is it far away? So that's our goal today, is figuring out how to figure out how far away stars are so we can start to say something about the size of the universe. Again, just by looking at these things, you can't tell. They could be close, they could be far away, they could be bright, they could be dim. So we need to figure out how to do this. And there's no label on any of the stars telling us how far away they are. So we have to figure out a way to kind of march our way out by knowing a little bit about all the distances in between. We should be able to figure out, kind of bootstrap our way up to the distance to the nearest stars. So the first step in the distance ladder is just to ask the question, how big is the Earth? Because if we knew how big the Earth was, we might be able to get a sense of how big other things are in the solar system. And I'm going to call up Celestia here very quickly just to get a picture of the Earth so we can see this here. We know the Earth is round and we know that it's a ball. And we can look at it from space and we can measure its size. But if you think about living on the surface of one of these planets like the Earth, trying to figure out its size, it's not obvious. If you go in very, very close, it looks flat. If you go further away, you can see that it's round. And so how did people living on the surface of the Earth determine that it was round to begin with? It's kind of a misnomer to think that people in antiquity thought that the universe was flat. They didn't. It was pretty obvious to anybody living by the coast that the Earth has a curvature to it, and that's because if you look at clouds coming at you from over the ocean, or here in Utah from over the West Desert, you see the tops of the clouds first, and then you see the full storm coming at you. So anybody who had spent any time observing their natural surrounding knew that the Earth had to be round, that there was a curvature to it. And the Greeks knew that the Earth was round, they reasoned that it was round, and they tried to think of a way that you could measure the circumference of this round ball just by making some careful measurements. And if we imagine, if you look at the planet Earth, if you look at anywhere on the surface, if you could somehow measure how quickly or slowly the Earth was arcing, if you could get some measure of the arc length of a piece of the Earth, and you could measure its size and you could measure the angular extent of that, you could figure out the whole circumference of the Earth by measuring just a part of it. So that's the idea that we want to work with, is figuring out how to measure the circumference of the Earth. And there was a guy by the name of Eratosthenes who was the first person to put this into play a little bit more than 2,000 years ago. And his thought was, if I could just, imagine having a dinner plate in front of you, and if you had a little wedge of the dinner plate, imagine just a little piece of the dinner plate that looked like this, that you broke off. If you knew that you broke off the dinner plate from the center, you could estimate the full size the dinner plate, even if you only had one little piece of it. And so his reasoning was, well, I'm living on a piece of the Earth. If I could somehow measure the angular arc of one little piece of this Earth, then I could measure the circumference of the entire thing. And he combined that idea with a piece of information that he knew from one of his friends. There was a place, he lived in Alexandria at the time, and he knew that visitors from a place called Sinai claimed that there was a well in Sinai that on the summer solstice, the sun reflected off of the water at the bottom of the well, that the light rays went directly down to the surface of the well. So this was a piece of information that he had from visitors who had traveled up to Sinai, that if the light ray came down straight into the well, that you could see the sun reflected on the surface of the water. So in other words, at the summer solstice, the sun was directly overhead in Sinai. So that was one piece of information. The other piece of information he had was that on that very same day in his town of Alexandria, if he went to the town square and looked at the column, there was a column that cast a shadow on that same day. Okay, so what that meant is that the sun was not directly overhead in Alexandria on the exact same day that it was directly overhead in Sinai. And that's exactly what you would expect from a round Earth, right? If the sun's really far away and we imagine the rays of light coming in parallel, then the shadow, you would get a shadow further north, where down further south you would not. So this was the information he had to work with, and he knew enough geometry to put together that if he could somehow measure the length of the shadow on that day, and he could measure the the height of the column, he could construct this little right triangle here. And that little right triangle, if I blow it up over here, here's the shadow of the column, here's the column itself, and here's the right triangle, that there was an angle that he could measure called theta, right, which he called theta. There's an angle you could measure by using the geometry of that, either by using a plumb bob or some kind of way to measure that angle. And because he knew enough geometry, he knew that if I had parallel lines, so here's a parallel line coming in like this, parallel line coming in like this, that this angle up here, which is something he could measure, would be equal to this angle down here, which is the angle between the towns of Sinai and Alexandria. So in other words, he managed to measure his relative latitude between Sinai and Alexandria, which was this guy right here. So by using this experiment with the column, he could figure out the angular difference across the planet Earth between Alexandria and Sinai. So now all he had to do then was figure out how far it was in actual distance from Alexandria to Sinai, and then he could equate those things, because he knew that the length of an arc, we'll call that S, the distance, the length of an arc on the surface of a circle is equal to the radius of that circle times the angle. So if he knew the angle from measuring it with the column, he could measure the distance by pacing it off, and he could get the radius. And he did that, and the only tricky thing was pacing off what he called 4,400 stadia, which were Greek stadium measurements, and that's very difficult to do because it was hilly terrain and they didn't have very good techniques for measuring distances like that. But to first approximation, he measured it to be about 4,400 stadia, and he got the circumference of the Earth right to within 10%. I think he determined it was 24,000 miles, and that's about what it is. Okay, so he figured out that the Earth was round, and he had a pretty good approximation of how big it was just by doing this simple experiment. So that was over 2,000 years ago that they managed to get this relative circumference of the Earth. Now, once you have the size of the Earth, that can be used to determine the distances to other things. So the next thing we want to do is ask the question, well, how big is the moon? If we could somehow figure out a way to compare the size of the Earth to the size of the moon, then we could figure out the distance between the Earth and the moon, because if we knew how big the moon was, we could get the distance between the Earth and the moon. So what situation arises where we can do that? Well, every so often the moon passes through the Earth's shadow, and I think I have a picture of this here. Yeah, every so often the moon passes through the Earth's shadow. This is called a lunar eclipse, and we have the moon going around on its orbit like this. Occasionally it passes through the shadow of the Earth, And if we know the size of the Earth, we know the size of the shadow, and if we know the size of the shadow, we compare it to the size of the moon. And we find out that the moon, or the Earth, is about 2.5 times the size of the moon. So just by doing that simple, just waiting and just looking at the relative size of the Earth's shadow to the moon tells us how big the moon is. If you know how big the moon is, you can figure out how far away it is, because once you have a known size, the farther away it is, the smaller it will appear to your eye. And so there's a mathematical relationship between how far away it is and how big it looks once you know its actual size. So once we know how big the moon is, we know how far away the moon is. So what this gives us here is we now have the scale model. We don't know how far away the sun is yet, but we do know that the Earth is this big, the moon is this big, and we know that the distance between them is something like 60 Earth radii. So this is something that we've measured. So this is an interesting situation because this allows us the opportunity to use this particular distance measure to figure out how far away the sun is. Now this is a tricky observation, and it took a long time to do this carefully, but if you wait until the sun and the moon and the Earth are in a configuration with that forms a right triangle, you can determine the distance to the sun by measuring an angle between the sun and the moon and knowing the size of the distance between the Earth and the moon. So this is a picture of what that looks like. This is, if we think back to our phases of the moon, you can try to imagine what phase this is in. This is the line between the sun and the Earth, right here. We have the line between the sun and the moon, and we wait until the moon is at a phase where the line between the sun and the moon and the line between the Earth and the moon forms a right triangle. So that forms a right triangle there, and what phase does that occur in? Well, let's take a look at that. We know that the new phase of the moon is between the Earth and the sun, so this is where new would be. We know that full phase is exactly opposite of that, and we know that our first quarter phase are at right angles to that, so this is first quarter, and this is second quarter. So in other words, this has got to be not quite waning gibbous, or waning crescent, but pretty close. So here's our waning crescent. So it's not quite to waning crescent, but if you are careful making careful observations, you can figure out exactly what fraction of the moon's surface you should be able to see, and you wait until that exact phase of the moon, and you get this configuration. Once you have that configuration, you have a right triangle. And right triangles are great because if you know an angle and a side, you can figure out the hypotenuse of that triangle. So if we look at this, we've got this configuration set up, and if we could measure on the sky between the sun and the moon that angle, then you could determine, once you knew the distance between the Earth and the moon, you could determine the distance between the sun and the Earth. So I wanted to illustrate this in stellarium so you can see what this might look like in the sky and how you might make this measurement. So let's go ahead and exit out of this, and I'm going to start up stellarium here. Okay, so this is today, and here we have the moon right here, and let's check what the phase is. The phase of the moon right now is it's just a little bit past full, so we're at a waning gibbous moon, and we need to get this to a not quite a crescent, a waning crescent moon. So I'm just going to go forward in time here. There it is. Okay. So here's our moon that's at this almost waning crescent phase. And you can see the moon right before it sets, and you can see the sun. So if you could envision a way of measuring the angle between the sun and the moon here, so if I could somehow imagine drawing a line between the sun and the moon, right, on the sky, and maybe I would just, as a first approximation, use my fist to know that a fist is 10 degrees. I could say that's 10, 20. We could get an angular separation of that distance between the sun and the moon, and that's a measurement that anybody could make. You don't need a telescopic observation to do that. And if you know that separation, then if you go back to our picture here, angular separation from where you're sitting is this right here. So this is that angular separation on the sky between the sun and the moon, right there. And that's something that you can measure without a telescope. We already know from our last distance step that this is the distance between the Earth and the moon, and because of that we know trigonometry. We can get the distance from the sun to the Earth. Okay. That's pretty exciting because that means that we now have determined the value of what we call one astronomical unit. If you remember, one astronomical unit is the distance between the Earth and the Sun, and that is equal to, from this measurement, 1.5 times 10 to the 11 meters. And let's pause for a moment and think about what this must have done to people's brains when they first realized this, because if you go outside in the night sky, you'll see that the moon is about a half a degree on the sky. If you go out in the daytime, you'll see the sun is about a half a degree on the sky. And so it's if you don't know the distances to these objects, they could be the same size, right? The sun's just this bright object and the moon's just this dim object. But once you know the astronomical unit, you recognize that the sun is enormous compared to the moon because it's so far away. And this must have just really blown people away to realize that the solar system was as big as it was and the sun was as big as it was. So once we have the distance between the sun and the Earth figured out, it's just a very short step to figure out the size of the solar system because we know Kepler's laws. Now, you have to remember that we probably knew a rough approximation of the astronomical unit for quite some time before Kepler came along, but once you know Kepler, we remember that Kepler tells us that p squared is equal to r cubed, right? R is a semi-major axis, and p is the period, right? P is period. Periods are easy to measure, right? Jupiter's period is 11.2 years. That means from this I can learn that Jupiter's distance from the sun is 5.2 astronomical units, 5 times further away than the Earth. That's great, but it isn't very helpful until you know how far away it is from the Earth to the sun. As soon as you know that, then you know that Jupiter is 5 times 1.5 times 10 to the 11 meters away from the sun. So because we have this Kepler's law in place, as soon as you know the distance between the Earth and the sun, you have the entire solar system. So these 4 steps give you, from measuring the size of the Earth to figuring out how big the moon is and how far away the sun is, gives you how big the solar system is. So this gets us out to our entire solar system for any object that we can measure in our solar system. However, our solar system is pretty small compared to the size of the universe. So the question is, how do we go from the size of the solar system to the distant stars? And that's where step 5 comes into play, which is how far away are the stars. Now we use this process called parallax, and something you've seen parallax all the time because you have 2 eyes, and anytime you have 2 eyes, if you close one of them and alternate back and forth between the other, you're seeing a slightly different line of sight from each eye. Now to illustrate that, put your finger in front of your eye like this, or in front of your face like this, and close one eye and look at your finger with respect to some distant background object, and then open and close the other eye and go back and forth like that, and you'll see it looks like your finger bounces back and forth with respect to the background. And the reason for that is because your right eye is looking at your finger from this direction and your left eye is looking at your finger from this direction, and so you have 2 different lines of sight. Now your brain synthesizes that information into a 3D image of what you see around you, and the reason it looks 3D is because your brain is using that parallax information to construct a 3D world that you perceive in your brain. Each eye is just telling you what it's seeing. It's your brain that puts all this together. So if we could somehow use the same properties of taking observations from different lines of sight, we could construct a 3D image of the nearby galaxy by using this property. So another place you might have seen this is if you're taking photographs. If you ever take a photograph and you maybe move with respect to the person, you'll notice that foreground objects tend to move a lot, middle ground objects move less, and faraway objects move the least. And you will have seen this probably more if you've ever been driving a car along the freeway through the mountains. The distant mountains look like they're staying put, the nearby stuff looks like it's moving past you slowly, and the really nearby stuff is going by very, very fast. Again, that's just the parallax property. What we'd like to do with the distant stars, though, is kind of construct, in a way, two giant eyeballs that can look at different lines of sight. So here is an example of the Earth in orbit around the Sun. We now know that 1 astronomical unit is the distance between the Earth and the Sun. That's 1.5 times 10 to the 11th meters. So we know what we call this a baseline. Call this a baseline. And if we take a picture in July, let's say we have a foreground star right here, that's this red star right here, with respect to these distant background stars. This foreground star, taking the picture in July, is going to look like it's a little bit off to the left because of the perspective of where we're looking. And again, if you hold your finger up and do that, you'll see that when you're looking with your left eye, wait a second. Sorry, this is July over here. Yes, good. Here's July over here. Yeah. Hold your finger out and look with your left eye, and you should see your finger bounce off to the right. If you look over with your right eye, which is over here, this is January right here, again, do that, you should see your finger bounce over to the left. So this star, this foreground star, just like your finger, is going to bounce back and forth with respect to the background stars. Now I can draw where it is in July on this picture. It's right here. And this difference on the sky is going to be this angle P, which is right here. Okay, so I should say that's going to be 2 times P, because this angle is this whole thing right here. So P is half of that. So you're going to be able to measure this angle, right? If you can measure this angle on the sky, if you know the baseline, again, we have a right triangle, like this, and we know the distance. Now the nice thing is the stars are so incredibly far away that we can use some properties of trigonometry to simplify this into a very, very basic equation. When you have a very, very small angle, all of the functions that you know of, like sine of the angle or tangent of the angle, they all just reduce themselves to the angle itself, right? So I can write down that the angle P is equal to 1 over the distance. And this is the relationship. The further away it is, the smaller the angle is. And the measurement unit we use for this is called the parsec. And the reason it's called a parsec is because at a d of 1 parsec, so if d is equal to 1 parsec, and I measure P as an arc second, and if you'll recall, an arc second is 1/60th of an arc minute, which is 1/60th of a degree. So if I measure P in arc seconds and I measure D as a parsec, then 1 parsec means 1 arc second. Okay, so something that's a distance of 1 parsec has a angular separation, angular motion on the sky of 1 arc second. And that's a convenient unit because it's very easy to measure the number of arc seconds a star moves, and then you can turn that into a distance by using this equation right here. So if I measure P, I can get D and vice versa. Now what is 1 parsec? 1 parsec, in units you might be more familiar with, are equal to 3.6 light years. So that's just converting the using the appropriate units to convert that into a distance that we know of. So 3.6 light years is about the distance to the nearest star, and that means the nearest star, Alpha Centauri, has a parallax angle of about 1 arc second. So it's a little bit challenging to see because an arc second is small, but it's not completely ridiculously small. Okay, so The next step then is to get some experience with this parallactic arcsecond stuff. So what we've got for our activity is this activity in parallax. So let me go ahead and find this here. It's in our activity book. The purpose of this, all you're going to need to do this activity is a meter stick, and that meter stick you're going to use to determine the relationship between the distance, how far away you move something away, versus the angular bounce that you get. And it's helpful to have someone to help you with this. They don't need to be somebody in the astronomy class, although they might if you want to find some folks to do that together. The first step is to determine the angular relationship between how far away something is and how much the angle shifts. So you'll do that just using a meter stick and your eyes as the baseline. So you'll have the distance between your eyes will be the baseline. So you've got your one observation this way and your one observation this way. And then the purpose is to apply that to solar system information. That solar system information is a diagram that looks like this. You're going to construct the diagram with the solar system and the nearby stars and figure out the relationship between our baseline here in the solar system and our reference star. And the other thing you're going to be doing in this activity is seeing what the limitations of this technique are. And you're, again, going to use your own eyes to do this, figure out if there's some limit where you can no longer detect parallax, because that's going to set a limit on how far away we can see in the galaxy. So that's the purpose of that activity, and I think it's pretty straightforward, something you can do with a friend. And just to put this in perspective, if you wonder why we are doing this type of stuff, there's a satellite called Hipparcos. Whoops, I should spell that right. Hipparcos, and it was called the Space Astrometry Mission. And this Space Astrometry Mission was literally to measure the stars, astrometry. And it was a space-based observatory that just did this one measurement. It looked at the stars in July and in January and tried to figure out the angular separation between the two observations. And this mission was launched back in 1989, so it was a little while ago, but pretty recently, all things considered. And it had a catalog of about 1 million stars. However, a lot of those stars are too far away to see the parallax for, so they did measure the parallax to quite a few stars in the nearby galaxy. And they got out to, if I remember correctly, let's see here. Yeah, 118,000 stars were charted with highest precision. Now you can go and see this catalog if you're interested. The Hipparcos Catalog is online, and it's a searchable catalog that lets you see all of the objects that they've taken with the Hipparcos Catalog. And let's see if I can pull this up here. Here we go. So one of the things that you can look at is, you can just submit the query and get every single star that they have, and this is all the stuff that they've measured, but the most important thing that they've measured is the parallactic angle, which is this parallax in milliarc seconds. So the measurement is 1/1,000,000th of an arc second, which tells you how precise this stuff is. And you can see how many stars they catalog with this, using the exact same technique that you're going to use on the surface of the Earth. Now this doesn't get us out very far. This only gets us out to, a few thousand light years. It doesn't get us out to the size of the galaxy at all. However, it does get us far enough out that we can measure enough of the stars to figure out their properties. Now the next thing we're going to do is talk about how we use this information to figure out the properties of the stars, but I think for now I'll let you go so you can work on your activity and use this parallax information for yourself.